Hello, this is section 1.3, day 2. We're going to continue evaluating limits analytically, and we're going to build some more strategies when we're tackling limits. So just a reminder, whenever you first approach a limit, try to plug the number in. That's your first strategy. If that does not work, you get 0 in the denominator or you get an indeterminate form, then we've talked about simplifying, factoring, conjugate, multiplying by 1, clearing the fractions, lots of different strategies. Now we're going to talk about some more today. So the first is the Piecewise theorem. And the whole idea is if you have a function h of x that's always less than g of x, and then you have another function that's always between these two functions, then for all in an open interval containing c except possibly at c itself, and if the limit as x approaches c of h of x equals L, the limit as x approaches c of g of x equals L. So notice the limit on these two outside functions as you approach c both equal L. Therefore, by the Piecewise theorem, then this middle function as you approach c must also equal L. So here's a visual to help you see that. So notice you have your h of x is always less than g of x. And f of x is some function that's between. So here at c, this would be your c, your x equals c here. You'll notice by the Piecewise theorem, all three of those functions approach the same L. Now, if ever you need this theorem in this particular class, the components will be set up for you. You will know you'll need the Piecewise theorem. That's not something that you'll have to just pull out of thin air and use that theorem. So, and I'll demonstrate that later. The other one are the special trig limits. And so limit as x approaches 0, sine of x over x equals 1. Graph this on your graphing calculator, and so you can visually see it. Also, and this is a benefit to watching the video, limit as x approaches 0 of x over sine of x is also equal to 1. And I'll put that on assessments. So it works either way, but graph this. When we talk about L'Hopital's rule in the future, I'll be able to show you how to solve this analytically, but for now, graph it. It's an accepted fact, limit as x approaches 0 of sine of x over x, or x over sine of x equals 1. And the limit has to approach 0. Same thing with this little fun special trig limit. Limit as x approaches 0, 1 minus cosine of x all over x. Okay, now this one, the reciprocal, I don't believe works, right? But for this one it does. So, but again, graph it so you can visually see. And then this one you may have discussed in pre-calc, but the limit as x approaches 0, this might look familiar. 1 plus x raised to the 1 over x is actually equal to e. This one doesn't come up very often, but it's a fun one to know. Right? But these two definitely. So you'll notice these limits look very similar to what we've been working on, but now we've got these new strategies to help us solve some of these. So you still tackle these the same way. The first thing you do is try to plug 0 in. Well, you immediately get 0 over 0, which is that indeterminate form. Okay, so now you go into your different strategies that you know. So can we factor this? Can we use the conjugate? I see a trig function in there. Can we somehow manipulate it, write it a different way? And up till this section, all those strategies aren't going to work. But if you look closely, if you factor a 2 out of that numerator and then pull a 3. So notice I wrote it as a scalar here in front. And now you can see that you have your 1 minus cosine of x over x, and you're approaching 0. So it meets those two components. So that means 2/3 is just a scalar. It stays out in front. And then this now, the limit of this is 0. So 2/3 times 0 is 0. There you go. So same thing here. At first glance, you can't plug 0 in. That's always your first step. It doesn't work. So, but tangent of 4x can be rewritten as sine of 4x over cosine of 4x. So notice I've pulled this cosine to the denominator. That's what I'm writing here. And then I have your sine of 4x and then your 6. So it's a little confusing, but what I've done is I had this sine of 4x in the numerator. But in order to use this special trig limit, notice it's x over x. So if I have 4x, I need a 4x in the denominator. And I have the x part that I need, but I need a 4. So what I've done is I've multiplied by 4 over 4, which is just multiplying by 1, totally legal. But now this part, I can plug 0 in, and I get 4 over 6. And this part turns into 1. So 4 over 6 times 1 is 2/3. So just fun little manipulation, but has to be legal. Make sure everything you do is legal. Also notice that I'm consistently writing the limit notation until I actually plug that 0 in. Until I solve the limit, you have to write your limit notation. Now, letter C here. This is one where if ever there's a fraction within a fraction, you usually will want to try to clear the fraction. So that's the first thing I did, was I multiplied by the common denominator. But what you multiply in the numerator, you have to multiply in the denominator to make it legal. So I distributed the 2 times change of x minus 2. That will wipe out that denominator in the numerator for us. So as I distribute, and you'll just have to follow along the steps, and then when you distribute the 5 here, beautiful things start to happen. You get to cancel your 10s, the change in x is canceled, and this is your nice reduced form. And notice I keep writing the limit notation. And then finally you can plug 0 in. Students who don't write the limit notation will forget to plug 0 in at the end, and they won't realize that they're done. They'll leave me this right here as the answer. So keep writing your limit notation. I will mark you off for not continuing to write limit notation. You have to make sure your math, I can follow your math steps. You need to be very clear with your communication. Right? And then over here, again, try to plug in pi over 4. That's your first step. If I plug pi over 4 in, I'll get, looks like 0 in the numerator. Yeah, you get 0 over 0. So, okay, well, you might think conjugate. You might think, well, this is actually kind of similar to what we just did. Tangent is sine over cosine. That's a fraction within a fraction. So that was my strategy, is let's clear out this fraction here. So multiply by cosine over cosine. So as you distribute, factor out a cosine in that denominator. Actually, I never distributed it. But if you factor a negative out, you get a common binomial that you get to cancel out. So here's your new reduced function, and now you can finally plug pi over 4 in. So it works. Okay? It is so important that you do your homework and practice these problems. When you watch me do them or see them worked out, you're like, oh, that's easy. Not until you go through and actually try them yourself. And if there's ever a step that you don't understand, like, Cogswell, how'd you jump from here to this step? Email me, okay? And we'll set up a time to Zoom, or I'll try to explain to you through email. Or, of course, you can ask it in class if I see you. All right, last thing, piecewise functions. So evaluate the following limits with piecewise functions. There is something that is so important that you want to make sure you remember for the future and for now. Whenever I ask you for a limit as x approaches some number, if it happens to be where that piecewise function comes together, you have to show me from the left and the right. Okay, please, please, please try to remember to do that. So, and notice, I want to know what the limit as x approaches 1 is, and that's where the two functions meet. So you have to show me that those two functions come together at the same point. If they don't, the limit does not exist. You are approaching a different value from the left and the right. So that's what you need to do. Limit as x approaches 1 from the left of our function, and notice I use the name, which is perfectly fine. And I'm going to know we're coming from the left, so I'm going to be referring to this top function, x cubed plus 1. You can plug 1 in, that's perfectly fine, you get 2. And the limit as x approaches 1 from the right of f of x, so that's going to refer to this bottom function here. You can also plug in 1 and you get 2. The fact that the two functions approach the same number from the left and the right means your limit is equal to 2. You need to use the proper notation to demonstrate this. Now, over here, limit as x approaches 3 of f of x. Okay, and notice again, it's where the two functions meet. So I need to see left and right. And as you approach from the left, it's actually -3. When you approach from the right, it's -1. Uh-oh, these functions are not coming together. Therefore, the limit does not exist. And you've demonstrated that. Now I put a little note down here. In this problem, had I asked you limit as x approaches 2 of f of x, then notice that's not where the two functions come together. So you just need to make sure you use the correct function. 2 is greater than 1, so you're going to plug 2 into this bottom function, and you get 3, and you're done. Now remember we talked about this is an exception, an accepted continuous function that you don't have to prove. So you can just simply plug 2 in. So it's only when the two functions, if it happens to be where the two functions come together. Okay. So please do your homework. Email me if you have any questions.